everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम कंप्यूटर ग्राफिक्स की क्लास करने वाले हैं जो कि क्लास नंबर आपका 8 है. ऑलरेडी हम 7 क्लासेस कर चुके हैं. सो दिस इज़ योर क्लास 8. Before these 7 classes, before 8 classes, that what we had cover up is your unit 1 we had cover up. We had completed that as well, and we had completed your unit 2 as well, and we had started in the last classes, that is your unit 3rd, that we will surely complete it in this class, which is your unit 3rd, that is your 3-dimensional. In the 3-dimensional we had completed many of the topic related to the oblique projections, and we will discuss the mathematical descriptions of the parallel projection. Here the isometric, diametric, trimetric, Cavalier cabinet that we had discussed about it. Now in this class we'll start with discussing about the new topic, that is your perspective projection. Before that, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In 3-dimensional, we'll start with, as I told you, about the perspective projection. The question that they can ask you in the terms of it, that is, what do you understand by the perspective projection, and also define the anomalies of perspective projection. And other question that they can ask you about related to the perspective projection is to derive perspective projection transformation matrix. So let's go ahead to discuss here. Perspective projection. So in this perspective projection, that for a perspective projection, object positions are transformed to the view plane along lines that coverage to a point and call the projection reference point, that is the center of projections here. When we have a viewpoint and the projection references, so from P1 and P2 that goes towards it and that merge and converge at a point, that is a projection reference point. And where a perspective projection produces the realistic view but does not preserve relative proportions as well. Projections of distance object that are smaller than the projections of object of the same size that are closer to the projection plane as well. Where in the same cases, if I'm going towards the mathematical description of perspective projection, where the perspective projection transformation is determined by prescribing that is your a center of projections and a view plane, and the view plane is determined by its view reference point, which is RO, and a view plane normal, that is we'll consider about N here, where the object point P is located in the world coordinate at x, y, z, and the problem is to determine the image point coordinate, where we have a coordinate like x dash, y dash and z dash as well. In the standard perspective projection, that here that the view plane of the xy plane and the center of the projection that is to be taken as a point of C, which is 0, 0, minus d, and a negative on the z-axis. So that will conclude here as to be in the form of in terms of the mathematical representation, if I'm talking about. So that is x dash equals to dx upon z plus d, and y dash equals to d dot y upon z plus d dash, and that is d here, and that is z dash is equals to 0. So the perspective projection transformation between the object and the image point in a non-linear and that cannot be represented as 3x3 matrix transformation. And if we use a homogeneous coordinate, that the perspective transformation that can be represented as a 4x4 matrix, and that we have here x dash, y dash, z dash and 1, which is equals to dx, dy, 0 and z plus d, that is equals to d 0, 0, 0, 0, d 0, 0, 0, 0, 0, 0 and 0, 0, 1D that has been multiplied by x, y, z, 1. So here normally to discuss about the perspective anomalies, and in the terms of it, that what we have to discuss in a detail. In the perspective anomalies, if I'm talking about here, that where the first perspective anomaly we have is your perspective for a shortening. So in this, that the farther an object is from the center of the projection, the smaller it appears. जितना दूर वो projection से दूर होगा object, वो उतना ही छोटा आपको दिखाई देगा. The second we have is your vanishing point. In the term of vanishing point, the projections of lines that are not parallel to the view plane that appear to meet at some point and the view plane, and that the common manifestation of this anomaly is the illusion that a railroad track meet at the point on the horizon here. The third we have is your view confusion. In view confusion here, that is the object behind the center of the projection that are projected upside down and backward onto the view plane. The fourth we have is the topological distortion. In the topological distortion, that consider the plane that passes through the center of projection and is parallel to the view plane, and the points of this plane are projected to infinity by perspective transformation, where a finite line segment joining a point which lies in front of the viewer to the point in back of the viewer and is actually projected to a broken line of infinite extent as well. Now we'll go ahead with another one that what we have to discuss here, and that is another question, and the question is to describe the one principal vanishing point perspective and as well as the two principal vanishing point and three principal vanishing point here. So the first we have here as to be follows. One principal vanishing point perspective, and that is we'll discuss about the two as well as the three. So one principal vanishing point perspective, two principal vanishing point perspective, and a three principal vanishing point perspective that we'll discuss here in the detail. Starting with the first, that is a one principal vanishing point perspective here, that the one principal vanishing point occurs when the projection plane is perpendicular to the principal axis, which is x, z, or z, y, x, y, z, and that assume it is the z-axis, and in the case of the view plane, the normal vector and in the vector k, then the principal vanishing point is, and that is of course we have here, which is your p3 equal, that tends to be x equals to a, y equals to b, and z equals to c plus d upon n3. In this, where A, B, C are coordinates of the center of projection, and N1, N2, and N3 are the components of the view plane normal vector, and a D is the proportional of the distance capital D from the view plane to the center of projection as well. The second we as I talk about that is the two principal vanishing point, where the two principal vanishing point projects occurs when the project plane intersect exactly two of the principal axis, and that is above that the perspective drawing with the two principal vanishing point in the case where the projection plane intersect the x and y axis, and that the normal vector satisfies the relationship that is n and k that is equals to 0, and of course the n3 that is equals to 0. So the principle of vanishing point, for that we have p1 and p2, and for that we have p1 is your x1 equals to a plus d upon n1, y1 equals to b, and z1 equals to c. And for the p2 we will be talk about it, that is your x2 equals to a, y2 equals to b plus d upon n2, and z2 is equals to c here. That is now we'll talk about the third one, which is the three principal vanishing point perspective. With the three vanishing point perspective projection that occurs when the projection plane intersect all three of the principal axes, which is your x, y, and z. And below the figure that we'll talk about it with the perspective drawing, with that three principal vanishing points in the cases where the principal vanishing points are p1, p2, and p3. So for that we had discussed about it and we had represented as well. So in the same cases that the p1 we have is x1 equals to a plus d upon n1, y1 equals to b, and z1 equals to c. The p2 we have is your x2 equals to a, y2 equals to b plus n upon d n2, and that z is equals z2 is equals to c. For the p3 we have here, that is your here that is x3 equals to a, y3 equals to b, and z3 is equals to c plus d upon n3 here. So in the same cases that has been VP and VP2 and VP3 has been represented in the form of that they are forming the hexagon and that they are coincide with one another here. Now we'll go ahead with other one, and that what we have to discuss as well, and that is a sort of a numerical part, which is the question is that the unit cube is projected into the xy plane. Draw the projected image using the standard perspective transformation. With the first we have d equals to 1 and the b part we have is your d equals to 10, where the d is the distance from the view plane. So let's go ahead with the question and then we'll go ahead with the detail about it. The question is the unit cube is projected into the xy plane draw the projected image using the standard perspective transformation where we have to find out d a equals to 1 and the b part we'll talk about d equals to 10 here, and that where d is a distance from the view plane here. So let's go ahead with the solution of this. In this we have a cube that is represented in the form of, okay, this is a cube, unit cube, so that is a 1 cube here. This is y-axis, this is z-axis, and this is x-axis. This is a ray line that is your A, B, C, D, E, and F. Okay, so this and G as well. So that has been represented here. Now we'll go ahead with the solution of this, and that to be as follows here. V equals to A, B, C, D, E, F, G, H. So that all we have here, that is H here. Okay, that is equals to, so what we have a matrix in the form that is A, B, C, D, E, F, G and H. So here we have first row, we have 0 1 1 0 0 0, and then we have 0 0 and 0, and that is your 1 and 1. The another row we have 0 0 1 1 1 0 0 1. The third row we have 0 0 0 0 1 1 1 1. The fourth row we have 1 1 1 1 1 1 1 1. So that has been represented here. Now for the that we have is your in the reference towards a perspective transformation. So that we have the matrix P for K, that is equals to D 0 0 0. Then we have 0 D 0 0. Then we have 0 0 0 0, and of course 0 0 1 D. Now for that that we had to talk about it, that is your first one, and that is a D equals to 1. For that we'll talk about it. So for D equals to 1, and that the per into V, and that is equals to, we have a matrix that is 0 1 1 0 0 0 1 1 0 0 1 1 1, and then 0 0 1. The third we have 0 0 0 0 0 0 0 and 0. Other we have 1 1 1 1 2 2 2 2 here. So here and then we'll go ahead, and that is your A dash is equals to 0 comma 0 comma 0. B dash is equals to 1 comma 0 comma 0. C dash is equals to 1 comma 1 comma 0. D dash is equals to 0 comma 1 comma 0, where E dash equals to 0 comma 1 by 2 comma 0, and F dash is equals to 0 comma 0 comma 0, and G dash is equals to 1 by 2 comma 0 comma 0, and H dash equals to 1 by 2 comma 1 by 2 comma 0. So that has been represented here. Now we'll talk about the second one, that is your D equals to 10 here. D equals to 10. The perspective matrix we have 10 0 0 0 0 10 0 0 0 0 0 0 and 0 0 1 10. Now with the same cases we have for dot V, and that we have the matrix here 0 10 10 0 0 0 10 10. The other we have row 0 0 10 10 10 0 0 10. Then another third row we have 0 0 0 0 0 0 0 0. The next we have 10 10 10 10 11 11 11 11. So that has been represented here. Now for that we have a coordinates as well. So that is the A dash will be getting as your 0 comma 0 comma 0. The B dash we have 1 comma 0 comma 0. The C dash is equals to we have 1 comma 1 comma 0. The D dash is equals to have 0 comma 1 comma 0, and the E dash is equals to we have 0 comma 10 by 11 0. F dash is equals to have 0 comma 0 comma 0. G dash is equals to have 10 upon 11 comma 0 comma 0. and h dash will be have, that is your 10 comma 11, 10 comma 11 and 0. Now we'll talk about the another one, and that what we have the another questions here, and that is using the origin as a center of projection, you have to derive the perspective transformation onto the plane passing through the points. That the points we have here r0, that is r x0, y0 and z0, and having the normal vector, that the normal vector we have n equals to n1i, n2j and plus n3k. So here in the same cases that we had talked about it, and for that we have a line axis x 0, y or z. This is your view plane, and where the vector we have, that is your n here, that is n equals to n1 I and n2j and 2k, and this is your comma p x comma y comma z here. So in the same cases, if I'm talking about with the detailed about it, and that is in respect towards it, that let p equals to x comma y comma z, and that the projected onto a p dash, that is the x dash, y dash and z dash, and the vector p o n p o bar p dash o bar, that the p dash o bar is equals to alpha of po, and that comparing with the components that we have, and the components that we be having is your x dash equals to alpha x, y dash is equals to alpha y, and z dash is equals to alpha z. And now finding the value of alpha here, that since any points p dash that we have is x dash, y dash and z dash, that lying on the plane is satisfying the equation, and that the equation that this satisfies your n1 x dash plus n2 y dash and plus n3 z dash, that is equals to of d naught, and putting the above value in the x dash, y dash and z dash, so that will get it out as alpha equals to d2 upon, sorry, d naught upon, so where is that is d naught is equals to upon, that is n1x plus n2y plus n3z as well. And for the projection transformation, that can be written in the form that the matrix we have is would be as follows, that p per n dot ro is equals to, which is your d naught 0 0 0 0 d naught 0 0 0 0 d naught 0 and n1 n2 n3 and 0. So this has been represented here. Now we'll go ahead with other question, and that is another question has been asked here, which is your to find the perspective projections onto the view plane where z equals to d, and where the center of projection in the origin is 0 comma 0 comma 0 here. So the view plane we have z equals to d, and the origin we have, that is 0 comma 0 comma 0. Now we'll go ahead with the detailed, that is the plane z equals to d is a parallel to xy plane, and thus the view plane normal vector n as the same as the normal vector k to the xy plane, and we'll talk about it, which is n equals to k, and that select the reference point as r0, that is 0 comma 0 comma d as well. So with the same references, we'll go ahead here, n1 n2 n3, which is equals to 0 comma 0 comma 1, r0 x0 y0 and z0 equals to 0 comma 0 comma d here, where the d0 equals to n1 x0 plus n2 y0 plus n3 z0, which is equals to d, and then the projection matrix we have here. D000 0D00 00D0 and then 0010. So now we'll go ahead with other question, and that what we have to talk about it, which is to derive the equation of parallel projection onto the xy plane in the directions on the projection that we have. So let's go ahead with the same discussion about it, which is we have is to be as follows. Direction of the projection we have ai1 vector plus bj vector plus ck vector. So what I'm talking about the k vector, so we'll represent it here as well. That is z-axis, that is the z vector, this is your x and this is your y. Onto this that we have, that is your px comma y comma z, and this is your p dash, which is x dash, y dash and z dash. So x dash, y dash and 0. And with this line we have, so with this line we have here, that is v equals to ai vector plus b j vector and plus c, that is k vector, that has been represented here. So with the same cases in this figure, we see that the vector v and p dash, that is we have the same directions, and this means the pp dash is equals to k of v, and that comparing the component we see that we will be having here is to be x dash minus x equals to k alpha, and where y dash minus y equals to kb, this is a, and then z dash is equals to z dash minus z equals to kc here, and that is we'll get which is k equals to minus z upon c, and where x dash is equals to x minus a upon cz, and of course the y, if I'm talking about the y, so that we'll find it out, y dash equals to y minus b upon c z here. Now we'll find out the matrix representation as well. So here we'll go ahead with this, and that we have the matrix as well, and the matrix representation. In the matrix representations we have, that is equals to 1 0 a by c minus a by c, 0 1 minus b by c, and 0 0 0. So that we can say here, that is your p dash equals to par v dot p. Now we'll go ahead to discuss the another question here. So here we'll go ahead with the other question, that is to describe the general form of the parallel projections onto a given view plane on the directions of the given projection v. So that we reduce the problems to the parallel projections onto the xy plane in the direction of the projection that we have, and that is your v equals to ai vector plus bj vector and plus ck vector, and by the 3 steps. So first we have to translate the view references point r0 of the view plane to the origin using the translation matrix, which is t inverse t minus ro, and that to perform an alignment transformation an, so that the view normal vector n of the view plane that points in the direction k of to the normal the xy plane, and the direction of the projection vector v that transform to a new vector, which is v dash equals to an dot v here. And the third that to project onto the xy plane using the pr v here, and then we have to perform the inverse of the step 2 and 1. So finally what we'll get it is to be as follows, p for. So here we'll go ahead with this, and that we will find it out as your pair, that is v comma n comma r, which is equals to t minus r not a inverse n pair v dot inverse, and that is an and t minus r here. So we'll find it out each and every matrix, and then we'll be finding out to solve it out as well. So here we'll be having t minus r naught is equals to 1 0 0 minus x naught, 0 1 0 minus y naught, 0 0 1 minus z naught, and 0 0 0 1 here. So now for that, the another one we will be having is your, that is the lambda equals to under root n1, that n2 square and n3 square here. So in the same cases we have here, that is your an here. The matrix for this we have lambda upon n mod minus n1 n2 upon lambda n naught minus n1 n2 upon lambda mod n, and then 0. The second we have 0 n2 by lambda n3 by lambda minus n2 by lambda and 0. The third row we have n1 upon mod n, n2 upon mod n, n3 upon mod n, and 0. The fourth row we have is 0 0 0 1. So this is the an here. After multiplying, what we'll get here is the form of in matrix, which is par vn r naught, that is equals to d1 minus an1 minus an2 minus an3 and ad naught. The second row we have minus bn1 d1 minus bn2 minus bn3 and bd naught. The third we have minus cn1 minus cn2 d1 minus cn3 and cd naught, then 0 0 0 and d1. So here, that is here. Now we'll go ahead with another question, which is to find the general form of oblique projection onto the xy plane, even though that has been asked many times in the examination paper. That will go ahead. General form of an oblique projection onto the xy plane. So in this, where the general form will talk about into the oblique projection here. In the same case, that the oblique projection that can be specified by a number of f and an angle 0, that the number f just prescribes the ratio that any line L that perpendicular to the xy plane will be the foreshortened after projection, and that the angle theta is the angle that the projection of any line perpendicular to the xy plane makes with the x-axis as well. To determine the projection transformation, we need to find the direction vector v. From the above figure, we have a line L of the length 1, and that we see that the vector p dash and p has been the same directions on the v. So that we have here is to be as follows, which is v equals to p dash p bar equals to x dash I vector plus y dash j vector and plus k vector here, and that is equals to ai vector plus bj vector and plus ck vector. So in the same cases, we have a1 equals to x dash, which is f cos theta, and b equals to y dash, and that is your f sin theta, and c equals to 1. So for where we have p and matrix v, that is 1 and that is 0 f cos theta, 0 0 1 f sin theta, 0 0 0 0 0 and then 0 0 0 1 here. Now we'll go ahead with other question that what we have to go ahead here, and in the same cases the another questions to be are as to be follows, and that is to find the transformation for, we have to find out the transformation for the Cavalier with 0 that is equals to 45, and B that the cabinet projection with 0 equals to, that is your 30 degree. So that what we have to find out. Let's go ahead with the question here. Find the transformation for the first we have Cavalier with 0 equals to 45 degree, and the B part is your cabinet projection which is 0 equals to 30 degree. So that we have to find it out. For the Cavalier projection, that is an oblique projection, and where there is no foreshortening of line perpendicular to the xy plane, and we see that for f equals to 1 with 0 equals to 45 degree that we have. So here for the Cavalier projection, and that the Cavalier projection is an oblique object where there is no foreshortening of the line perpendicular to the xy plane, as I told you about it, and we then see that f equals to 1 with 0 equals to 45 degree what they had mentioned here, and for that we have a matrix that is par b1 that is equals to 1 0 root 3 by 4 0 0 1 1 by 4 0 0 0 0 0 and 0 0 0 1. And that is the another one for the cabinet 0 equals to 35, where the cabinet projection is an oblique projection which is f equals to 1 by 2 with theta equals to that is your 30 degree here. And then we have here is to be as follows, that is your the matrix is your par v2 equals to 1 0 root 3 upon 4 0 0 1 1 by 4 0 0 0 0 0 and 0 0 0 1 here. Now we'll go ahead to discuss about the another thing, that is your what do you mean by 3D clipping. You have to discuss in detail, and the other question is you write a short note on a 3D clipping, so that what we'll discuss here. This has been asked of 10 marks, so you have to be very well prepared about it. In a 3D clipping, that an algorithm for the three-dimensional clipping identifies and saves all surfaces segment within the view volume for the display onto the output devices. All the parts of the object that are outside the view volume that are discarded, and clipping in 3 dimensions that can be accomplished using the extensions of 2-dimensional clipping method. Instead of clipping against straight line window boundaries, we now clip object against the boundary planes of the view plane, a view volume. And to clip a line segment against the view volume, we would need to test the relative positions of the line using the view volume boundary plane equation as well. By substituting the line endpoints coordinate into the plane equation of each boundary in turn, we could determine whether the endpoint is inside or outside the boundary. And endpoint x comma y comma z of a line segment is outside a boundary plane if ax plus by plus cz is plus d, that is greater than 0, where abc are the planes parameter for that the boundary. And similarly, if the point inside the boundary, if like ax plus by plus cz is plus d is less than 0, so lines with the both endpoints outside a boundary plane that are discarded, and those with both endpoints inside all boundary planes are saved. And the intersections of the line where the boundary is found using the line equation along with the plane equation, and the intersection coordinate x1 y1 and z1, that are the values that are on the line and that are satisfying the plane equation, which is ax1 plus by1 and pz1 plus d equals to 0. To clip a polygon surface, we can clip the individual polygon edges, and first we could test the coordinate extents against each boundary of the view volume to determine whether the object is completely inside or completely outside that boundary. If the coordinate extents of the objects are inside all boundaries, we save it. If the coordinate extents are outside all boundaries, we discard it. And all the objects within the view volume map to the interior of the specified projection window. The last step is to transform the window content to a two-dimensional viewport, and which specifies the location of the display and onto the output devices. The clipping in the two-dimensional is generally performed against an upright rectangle, that is, the clip window is aligned with the XY axis, and this is greatly simplifies the clipping calculation because each window boundary is defined by one coordinate value, and for example, the intersections of all lines that crossing the left boundary of the window have an x coordinate, and that is equals to the left boundary as well. With the same case that the viewpoint view volume clipping boundary, that are planes whose orientations depends on the type of projection and the projection window and the positions of the projection that reference a point as well. Now we'll go ahead with the detailed about it, which is another question, and that is termed as your write a 3D line clipping algorithm for the Cohen-Sutherland region code method, and that is has been asked many times in the examination paper of 10 marks. So we'll go ahead with 3D line clipping algorithm for Cohen-Sutherland region code method. So for that, the Cohen-Sutherland algorithm extends easily to a 3D. It extends the 3D clipping window boundaries to define 27 regions and assign a 6-bit code for each region, that is for each point x, y, z. And suppose the bands for the cuboid view volume, that are x x min and x max, y min and y max, and z min and z max, where the subscript v min and v max stands for the view volume min limit and view volume max limit front of the back end planes as well. We assign bit codes to any point x, y, z, and for that we have here bit 1 equals to 1 if x is less than x min, bit 2 equals to 1 if x is greater than x max, bit 3 equals to 1 if y equals to y min, bit 4 equals to 1 if y is greater than y max, bit 5 is equals to 1 if z is less than z min, and bit 6 is equals to 1 if z is greater than z max. So in the same cases, otherwise the bits are set off to 0 as well, and a point is inside if the region's code is 0 0 0 0 0, and therefore it's a line of visible, and if both ends as 0 0 0 0 0, then of course the line is visible. And if it lies entirely to the side of the clipping region, that is if the logical and operation that onto the bit code of the end points are the non-zero here. So that we had end up here. Now we had end up with unit 3rd that we have to discuss about it, and even though that we had completed here. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button, and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In the reference towards computer graphics, what we had covered up is we had covered up unit 1, unit 2, unit 3, and what we have to cover up is the next coming units here, that is your unit 4 here. And as well as in the reference towards it, I will discuss about unit 5 as well, but unit 5 is not included in the computer graphics, so we'll do ahead only the unit 4, and then we'll starting with a very short answer type questions here. That is In the unit 1, that is your graphic devices, we had completed the introduction and line generation, types of computer graphics, graphic display, random scan display, raster scan display, frame buffer, video controller, point and lines, line drawing algorithm, circle generating algorithm, midpoint circle generating algorithm, and a parallel versions of these algorithm as well. With the same reference, this unit 2 transformation we had covered up with, that is your transformation, basic transformation, matrix transformation, and the homogeneous coordinate composite transformation, reflections and shearing, windowing and clipping, and that viewing pipeline, viewing transformation, 2D clipping algorithm, line clipping algorithm such as Cohen-Sutherland line clipping algorithm, Liang-Barsky algorithm, line clipping against non-rectangular clip window, polygon clipping, Sutherland-Hodgman polygon clipping, Weller and Atherton polygon clipping, curve clipping, and text clipping that we had covered up. In the next coming class, we have to cover up the unit 3rd, which we had covered up, that is your 3-dimensional. In that, we had covered up the 3-dimensional, 3D geometric primitive, 3D object representation, 3D transformation, 3D viewing projection, and 3D clipping as well. In unit 4, we have to cover up with the curves and the surfaces, which is your curves and surfaces, quadratic surfaces, spheres, ellipsoid, blobby object, introductory concept of spline, B-spline, Bezier curves and surfaces, hidden lines and surfaces, as well as back face detection algorithm, depth buffer method and a buffer method, scanline method, basic illumination models, ambient line, diffuse reflections, spectacular reflections, and a Phong model, combined approach, Warn model, intensity attenuations, color consideration, transparency, and shadows as well. And after that, we have to cover up the very short answer type question as well. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Other than the computer graphics, we are doing data warehouse and data mining, managerial economics, database management system, reasoning, which we had where we had completed the verbal reasoning and non-verbal reasoning we had started with, and principle of programming languages we had completed, and we will start with quantitative aptitude as well. So thank you, hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Thank you.